Hi, welcome to the problem session for chapter 10. Chapter 10. This is the Rankine cycle, steam power cycles. So we'll go ahead and work through a couple of problems here. We'll start off with a simple Rankine cycle. Then we'll do some modifications to improve efficiencies. We'll look at reheaters. We'll look at regenerative heating with feed water heaters as well. So let's go ahead and just start off with a simple Rankine cycle. And one of the first things you might be kind of curious about, I guess, is what are typical operating conditions. So let's look at, go online here and see what a typical steam turbine operating conditions are. So one you might be able to buy, like GE sells steam turbine systems, and see what Google has here to tell us about this. And got a couple of there are two models here. So let's go ahead and look at their 200 series here, steam turbine. And there's all sorts of interesting specifications you can see on this and the size of what they operate on. But what I kind of wanted to get at was down here. You see the main steam operating conditions, and it can go up to 2,000 psi and 1,000 degrees Fahrenheit. So that'd be kind of the maximum. So let's go ahead and we'll start off with a simple Rankine cycle with those operating conditions. So I don't like looking up values in tables. I'm going to go ahead and open up EES so we're not constantly going to the tables and doing interpolation. To do this will make it a little bit quicker. So I'm going to go ahead and open up a EES file here, and so this is in English units. I'm going to go ahead and set my unit system. I'll just go ahead and do it up here at the top so it's obvious. This will be English. We're going to do our units in PSIA and degree Fahrenheit to go ahead and do that. So that's just sort of a directive there. So let's go ahead and put in our these conditions here. So I'm going to define the high pressure. I'll call that pH. We'll do that at 2,000. That's in PSIA. And then we know our high temperature, so we'll call it TH. And that's going to be at 1,000. And there's one other specification you need to know for Rankine cycles, which is what the low pressure is in the cycle, and that's determined by what the temperature is going through the heat exchanger. So it's really a function of how cold your cooling water is and how effective it is. Those are usually specified in these kind of thermodynamic problems because it's sort of a heat transfer question. So we'll just we'll kind of make something up. It might be typical. So I'm going to do my low pressure down here at 20 psia. They can often get colder than that if you got good cooling water, but we'll go ahead and operate with that. So those will be our three parameters. And so I'm going to put my solutions down there, and we'll go ahead and now it's just we'll do our basic Rankine cycle. So for example, this will be the setup we'll use, your typical 1, 2, 3, 4 with our condenser, pump, boiler, and turbine. So let's go ahead and put those into our EES file over here. So first thing is we'll ignore pressure drops. So we'll have some isobaric steps. So we'll assign our pressure point. So for example, P1, which is the low pressure going into the pump. So we'll make P1 equal to PL. All right. And then the pump is going to go up to P2. So P2 is going to be equal to P high. So I'll go ahead and do that. And then I can specify my other two pressures, because if I ignore pressure drops, P3 will be equal to P2, and I know that P4 will be equal to P1. So I've got my four pressures. I'll open up my array table so I can start to look at that. Kind of nice to see all the points and see what intensive variables I have. Okay, so we've just kind of done some specifications, and there's one other assumption that you can make with Rankine cycles. Remember, this is from the design of the condenser. We know that the condenser outlet, what we're going to have is a saturated liquid. So we can say that X1, the quality coming off the condenser, we know that that's going to be equal to 0. So that should give us another column in our array table here. So we've got that. In fact, now we see we got two values at 0.1. 0.1 is completely specified. So with this, what I normally do is just go around the cycle from some point that I know. I can start at 1 because I completely know that, and move through. So first thing we'll do is we've got an isentropic pump. That means the entropy doesn't change across it. So I can define my entropy at 0.1. My material here is, we're going to do a water. And P is P1, and I knew X1. And then I know that S2 is going to be equal to S1 because it's isentropic. So just give me another column in my array table. There we go. From points 1 and 0.2. And then we'll go ahead and keep moving around. So we can go over here to 0.3. This is going to be our boiler. All right. And we know that the temperature at 3 is that high temperature, so T3 is equal to T high, right? That'll give me yet another column in my array table there. Remember, anytime I got two values in a row, it's completely specified. I only got one left, which is 0.4. I'm going to do is an isentropic step through there. So we're going to have an isentropic turbine. So let's go ahead and have ES look up our value of entropy at 0.3, water, and we know P3 and T3, and then we know S4 is equal to S3. All right, so looking at my table here, I've got two values in all lines. In fact, I have a pressure and an entropy at all points. So now we can go ahead and calculate what our efficiencies are. When we need efficiency, we need to know the enthalpy values. So let's go ahead and just have EES look up our enthalpy values. And actually, we just got four points, and I can actually just do this in a loop. So just to save some typing, I'm gonna make a loop from 1 to 4 and have it look up the enthalpy at every point. Enthalpy of water using P and S. I could write this on 4 lines. It just kind of saves me a little time. That should go ahead and give me yet one more column. My enthalpy values there at 1, 2, 3, and 4. So then we can go ahead and determine our efficiency. So we can find out the heat input, that's between 2 and 3. So that's going to be H3 minus H2. And then Q out is going to be equal to H4 minus H1. That's in the condenser. Do a little quick sanity check here. Q in is greater than Q out. They're both positive values, so I didn't flip one of those directions, which is good. So now let's just go ahead and find our efficiency. I'll call that eta. I'll do 1 minus Q out over Q in. All right, and there's my efficiency at 33%. All right, so let's actually, which is actually pretty good for a Rankine cycle, for just a simple one. But there's something I kind of want to look in here, which we haven't necessarily looked at. But one of the reasons why that efficiency might not be so easy to achieve in practice. So what I'm going to do is I'm going to go ahead and I'm going to plot this on a TS diagram. So what I'm going to do is get my values of T and S on here and put it onto a property plot. So I'm going to go ahead and under plots, I'm going to create a property plot. I'm going to go ahead and create that of water. I'm going to select TS, which is the default there. I'm going to draw just 2 isobars, which will be my high and low pressure, so we can see where those are, which was 20 and 2000. I don't need any other pressures. And this is just to keep the plot kind of simple. I'm not going to put any values of V on there as well. And this should give me, there's my TS diagram. Oops, xenon, wrong material. I meant to specify water. Let me go ahead and redo that whole thing again. Sorry about that. Yeah, I selected the wrong material. Same thing, just meant to put water, not xenon. Clearly, if you got a power plant operating with xenon, be much different than what we're doing here. Be pretty expensive, that's for sure. Okay, all right, so let's go ahead and we got this right now. Now we have water here. Okay, that's what I expect. So there's our TS diagram. We see our 2 isobars for our high and low pressure. And what I can do now is I can plot those points 1, 2, and 3, and 4 on there. So if I come back here, I need to get though the temperature at 1, 2, and 4. I've got all my entropy values. So I need to come back over here. And for example, T1 is the temperature of water at P equals P1. I think I knew 0.1, and then what else do I need? I needed 2 and 4, and those I can do with P and S. So T2 is temperature of water, S equals S2, P equals P2. Remember the ordering, that doesn't matter. Copy and paste that to do 0.3 because I'm doing the same thing. Not doing a loop here because I'm not doing all the points and not using all the same variables. Oops, I meant T4, not T3. You need to catch me on that kind of stuff. Okay. We got now. Okay, so now I've got a T and an S value for all 4 of the points. So I can come back to my plot and I'm going to go ahead and overlay, which means I'm going to overlay the points. And I'm going to go ahead and put the x-axis is S, the y-axis is T. We'll go ahead and plot that in red and make it show up a little bit better. Okay, and so here what we've got, this is showing the process. Now there's a couple things. All it's doing is connecting with straight lines all of those points. So let's kind of look over here. This is 0.3 up here in the upper right. That's our superheated vapor going through the turbine. 0.4. So this is point 1 is the condensation. 1 and 2 are almost right on top of each other because that pump doesn't really have much. Remember, the backwork ratios are really small. So 1 and 2 are like right on top of each other. And then in actuality, it doesn't follow that line. It kind of, so I think I can draw on here. What it's actually doing is it's going to go up that isobar line across there and up to there. That's actually what it does. But anyway, we can see where the points are. So okay, so now the point is really good efficiency. The reason it has such good efficiency is it's actually pulling a lot of energy out because we're getting a condensate in our turbine. Now remember, we don't want condensate inside the turbine. That's not good. In fact, we kind of got a web page over here, which is kind of interesting. Kind of talks about condensation in turbines, which is effectively shorting the TLDR on this is that you don't want it. It's really bad. And here they're kind of showing pictures of condensation in turbine blades. And they mention here, these high speeds, these water droplets have the force of machine gun pellets. And they act like solids more than liquids. Essentially, it's going to destroy your incredibly expensive turbine. We don't want that. So let's see, to make this more realistic, how we could operate here and not have it. Now, we can't make it any hotter. Remember, I set that at the highest temperature and highest pressure that the system could operate on. So what I want to do is I want to move that point over. Effectively, I want to move this over somehow to the right so I can get this point over to the right somehow. Should we like to move it? And what do we do that? We can do that, if you remember, we can do that with reheaters. So what we'll do is we'll add a reheater and see if we can pull that point over to the right. So let's do this. We're going to modify our simple Rankine cycle. We're going to add a reheater like this. So right now we're going to go up to 0.4, but now we'll go ahead and reheat it to 0.5 and 6. So we're going to introduce 2 new points going through the reheater and coming down over here. So and let's see how this affects our efficiency and also see how this affects moving this across. And just kind of as practice, so I'm going to go ahead and we'll just, instead of modifying that file, we'll just go ahead and open up a whole new EES and step through this. Be a little quicker this time, probably a good review on how to do it. And we're going to go ahead and do our reheating system. So most of these steps will be the same, but we'll go ahead and just do them again just for quick review. So I'm going to set my unit system to English, PSIA, degrees Fahrenheit. All right, and our P high was equal to 2000, and our T high was equal to 1000, and P low was equal to 20. And then we also knew that the outlet of the condenser, which is going to be X1, it's still 0.1 on our diagram, is equal to 0. So let's go ahead and all we've done is X so far. So now let's go ahead and we'll do our isobaric steps. All right, we got a couple extra steps now. We're gonna have a total of 6. So let's start off with, we'll just start at 0.1. So 0.1 is the low pressure, and 0.2 is going to be equal to the high pressure there. So P2 is at point high. And then what we know now is going through the boiler, no pressure drops. So P3 is going to be equal to P2. All right. And now we've got this intermediate pressure where we're doing reheating. So let's add a value up here. We're gonna, I'll call it PM for P mid. It's gonna be something between 2000 and 20. I'll just go ahead and put 1200. I don't know what it's gonna be, maybe something around the middle there. There's no way you can know this necessarily ahead of time. It's not like a Brayton cycle where you could go ahead and do the square root or the geometric root of it. At this point, so it'll be something in the middle. We'll just do that. So this tells me that P4 is now going to be equal to that middle pressure. Knowing pressure drops, P5 is going to still equal to be P4. And then finishing out of the turbine, we've got P6 is now going to be equal to P low. All right, so that should be all of my pressures. Let's check our table here. All right, so I got 0.6 points on there, and we've got our 6 pressures. So once again, I'll go ahead and just move through the cycle. I've got 2 things right here at the beginning. So remember, now first thing, we'll just go ahead and go through our pump here, which is going to be isentropic. I'll put that on here as a comment, isentropic pump. All right, and S1 is going to be the entropy of water, P equals P1, X equals X1. All right, and we know that S2 is equal to S1. Okay, I like to kind of periodically just keep solving, making sure I didn't do some sort of typo. That way you know where your error is. It's whatever the last line is you did. There we go. So we got a new column with our entropy. And now we're going to go ahead and let's move through our boiler. It's the next thing around. So boiler. And what we know is that T3 is equal to T high. And that should give us yet another column in our table here. Just again, double checking it. There's my temperature. All right. So then we're going to go through the turbine, assuming that that's isentropic turbine. We can now go through there. So going from 3 to 4. So we know that S3, we'll have it, ES, look it up, entropy of water at P3. And what we know there is T3. And then we know S4 is equal to S3, right? And there's our next entropies. And in fact, it's going to keep going because we're then going to go ahead and go to 0.4 when we reheat, and then it's going to be at 0.5. We actually don't have any entropy between 5 and 6. So now we got to go through the reheater, all right, and so that's going to be 0.5. So we're going to say T5. We'll assume it goes all the way up to that high temperature, reheating to T5, that T hot. And now we can go ahead and get the entropy at 5 to make that isentropic turbine. It's not the same as 3 and 4 because it's added heat to it. So now we're going to have our low pressure turbine, essentially what that is. And so first we'll have S5 entropy. What we knew is the pressure, and we knew the temperature, and we know that S6 is equal to S5. All right, so now we've got S and P at all the places. So we're done with this. We're going to do just like we did before. We can go ahead and find our efficiencies. And in fact, I could probably just copy paste off my other slide, couldn't I? What did we do here? We're going to be doing essentially the exact same thing. I'll just copy and paste in the interest of time here, right? Because what I'm going to do is I'm going to have it look up all the enthalpy values using P and S. And actually now I'm going to have 6 points in there. And then actually I'm going to go ahead and let's just double check that. We're going to have to modify that efficiency equation. We'll talk about that here in a sec. Okay, so just give me another column. There's all my enthalpy values. Okay, so then what we're going to do is we've now got our efficiency, but one of the things we want to do is we're going to have to modify. So the input, right, okay, now is between 3 and 2. That's true, but we need to add the reheating, which is going to be between 5 and 4. So Qin is going to be 3 minus 2. I'll go ahead and put a couple parentheses around it just to make it clear. So I've got that heat input plus, and now I've got H5 minus H4, because there's extra heat going into it. Heat output is now not 4 to 1, it's actually now 6 to 1, right? Because that's actually going to be through the condenser. And so, all right, so good quick sanity check. Q in 13, Q out 890, so it's bigger than that. I got an efficiency of about 35%. Let's go ahead and compare that to what we had before. 35%, 33%, not a whole dramatic change. But remember, the main point of what we were trying to do here was see if we could pull ourselves out of that saturation region, so we're not getting condensation in there, the mixture region. So we'll go ahead and do a property plot again on this to kind of just look at what it looks like. Good kind of practice here. So plots, we're going to do, these steps are all the same. I'm going to do a property plot. I'm going to do it with water this time, hopefully not xenon. We'll go ahead and do our pressure. I'll go ahead and add a third pressure line on here now because we've got, we did one at 1200, right, and which is our intermediate pressure in 20. Go ahead and get rid of the other lines. Don't need those. Keep it clear. Won't put volume lines on there. Okay. So here's my TS diagram. I see my intermediate pressure on there. I can overlay plot. Now I need the temperatures again. We did everything but 3 and 6. So I need to do it again. I'm not going to do a loop just because that's not going to be all of them. So T1 is temperature of water. P equals P1. S equals S1. Right? Okay. And I need that at 2, 4, and 6. So 2, 4, 6. So that's 2, 4, and 6. Okay, and now I've got all my TS, so now we can do an overlay plot on there. So plots, overlay plot. We're going to do S and T. I'll do it in red again so I can go ahead and see it. S and T, it should be right. So okay. So again, now I've got my oops. Go back. I got small. Okay. Here's my TS diagram again, and you can see the reheater up here on the top. Remember again, the point 1 to 2 is going to be following that high pressure isobar. 1 and 2 is right on top of each other. But notice I pulled it to the right. We can actually look at our other one quickly if we want to look at where it looked like. Right, so notice it was down over here. We've moved it to the right, but not quite far enough. So what we need to do, you realize, is we need to move it to lower and lower pressure. So I could keep guessing lower and lower pressures to actually get it over to the right. So let's just go ahead and make this 800. Actually, let's do this. This will actually be interesting. I'm gonna go back and leave what that is. We'll actually have EES find that exact pressure for us. So what I'm going to do is I'm not going to specify that middle pressure, all right? So now it's not going to know what the middle pressure is, but what I'm going to do is I'm going to say that point is on the curve. And so what I'm going to do effectively is what I want to say is that the quality at point 6 is a saturated vapor. So what I want to do is I want to say X, oops, where am I typing? Come back over here. There we go. Okay. What I want to do now is I want to say that X6, all right, is going to be equal to 1. So I'm specifying what that is at 0.6. And I'm going to have EES solve for what that middle pressure is. So I've now specified what X1 is, but I haven't specified the pressure. Oops, hold on a sec. Okay, so where were we? Okay, so what we were looking at was okay, so we're fixing 0.6. We're saying we want that to be a saturated vapor, but we don't know what that middling pressure is. So we don't know essentially what P6 is. So what we need to do now is need to give it some more information. We have to essentially tell EES know that X6 is the quality at 0.6. So let's come and look here. 0.6 was coming out of our low pressure turbine, which was the entropy where we're doing that isentropic step. So now we can say that entropy has to be out of a saturated vapor. So eventually we're going to say S6 is also equal to the entropy of water. And we know what P6 is. That's the low pressure. But now we're going to say is that the quality is equal to X6. And so I think that should work. All right, so what we've done now is solved for what the middle pressure is by forcing that point onto the diagram. So let's go ahead and actually we'll do another overlay plot here. With these new points on it. So I'm going to do again a TS diagram. We'll do this one in green with the new points. I think that's all I need to specify there. Okay, so here's my green line, and now we can see what it's specified at. And we see we've moved this over a little further to the right, and there's my point 0.6, which is right on the curve. So if I go and look now, I can see ES solved the middle pressure for me. 524.6, right? So it's a lot better than doing a whole bunch of guessing. We know exactly that if we want that pressure, essentially 525 psia. All right. So what we'll do now, now that we've done this, is we can see if we can kind of increase the efficiency. So what we'll do is let's look at a reheater. So we'll go ahead and put a reheater on here, and then we'll take a look at that. So I'm going to go ahead and take a quick break, and then we'll come back. All right, we're back. Okay, so what we want to do is we're going to look at increasing the efficiency with a reheater. So we'll go ahead and operate with this system here. So let's look at this system here. So it's just yet another modification. We've got our reheater, but now what we're going to do is we're going to add an open feed water heater. So I'm going to branch off at 0.4 and run that to an open feed water heater. That's at middle pressure. And so we're going to have 2 pumps down here. So we've now got 8 points. So let's go ahead and see how this affects our efficiency. And once again, I'm going to go ahead and open up another EES so we can always kind of go back and look at those other ones if we want to refer to them. And we'll now solve this problem here. Okay, and so, in the interest of time, we've gone through two of these from the beginning, and this is a modification of what we did before. We can actually, let's go ahead and just start with what we did before without the reheater. We'll modify it for what we've got in our problem now. So what I did there was I just this is just the previous problem we have. So we're gonna modify that. And so what I'm gonna do is some of the stuff here at the end. Let's go ahead and we're gonna comment that out because as we're working through this, we may not have all those values. So now let's look at how we wanna modify this with this property here. So now we've got two pumps and we've got a couple new states on here. So first of all, looking at let's go through and look at what we've got in terms of our specification. And what we'll do actually, we'll just go ahead and specify our middle pressure. What was that good middle pressure? 525. So we'll go ahead and we'll just set that at 525. So we know that's what that needs to be. And not do that specification stuff that we did before. So I'm going to get rid of that. And I think that was this line right down there. So let's just make sure. All right. So okay. So more or less it just it'll clean things up a little. Same problem we've got. Okay. So now what we need to do is modify this, and we've got two new states. We're gonna have a 7 and an 8. So let's look. We start off with, let's look at all of our isobaric steps. So 0.1. And notice 0.1 is not the low pressure anymore. Actually, if you look at that, 0.1 is actually going to be equal to my middle pressure, right? Okay. And 0.2 is the high. That's still the same. 0.3 is 2 isobaric. 4 is our middle pressure. 0.5 is 4. That still stays the same. 0.6 is going to be our low pressure. And now what we do is we've got two new states, 7 and 8. So let's do those pressures. So we now got P7 is P6, or our low pressure. And then P8 is equal to that middle pressure because we've got now two pumps in there. So let's see if we've got we should have 8 lines on there. Okay, so we've got all of our pressures. So we'll just kind of move through the file here, modifying as we need to. So we put in those extra pressures. So now here we'll go to our pump. So let's look at our low pressure pump here. So I'll go ahead and just remind myself now this is a low pressure isentropic pump. And actually now what I've got is this condenser outlet is 0.7. So if I come back up to the top, it's not X1 that's 0, it's X7 that's actually going to be 0. And then this entropy here, this will be S7, because that's the inlet to that low pressure pump. And I know that S8 is now going to be S7. All right. I wonder if this is going to, okay. So there we're moving through. So we've fixed our low pressure pump. We've got two things at everything but points 1 and 2. So we're actually almost done with this problem. We just need to do points 1 and 2. So that's over there on that high pressure pump. And so notice we know the pressures, but we don't know another intensive variable. So there's two other things we need to determine to do it. And well, this is, if we assume that pump's isentropic, we know that those entropies are the same. So I just need to find one point and then equate the entropies of it. And what I do have this new component, my feed water heater. And so if I do an energy balance around that will go ahead and give me another equation. So I can go ahead and make that specification. So let's go ahead and add our feed water heater. Okay. And this is going to be an energy balance over that. So the energy that's going in, so we've got a fraction y coming through. Let's just say our fraction y, we'll pull 20% off. We'll go ahead and look at that. But let's go ahead and pull off 20%. So we'll call y is 20. So that means that the energy balance over there is going to be y times H4 going in. The other thing that's going in is what's coming through the condenser, which is going to be 1 minus y times H7. And that's all equal to H1. Now notice what I've done now. This equation here is going to go ahead and specify what H1 is. That's going to give me a point at 0.1. And then, now I know everything at 0.1, I can go ahead and make that an isentropic at 0.2. Okay. Now, however, I haven't looked up all those EES values for enthalpy. So actually this will tell me I don't have enough equations yet, because I haven't specified those enthalpies, but I commented out the looping of the enthalpy. I'm not going to do them all. Let's just go ahead and have it look up 4 and 7 for me to go ahead and so I can solve it there. So H4 is the enthalpy of water. Let's just write that P4 and S4. S equals S4 and 7, because those are specified, and then it should be able to solve this for H1. Okay, so now I should have another column. There's my enthalpy value. Now notice I've got two things at 0.1, and that's going to go ahead and I can look up my entropy value and put it down at 0.2, and I'll be done. All right, so let's go ahead and do our high pressure isentropic pump. All right, and so we can go ahead and look up S1, and it's going to be water. We know the pressure, and then the energy balance gave us enthalpy, so that's H1, and we know that S2 is equal to S1. That's that isentropic pump. Now here's my new system. I've got all of my pressures and all of my entropy values. So let's go ahead and look at what our efficiency is going to be. So now we can go back to that parts here at the bottom. Again, we'll need to do some modifications. All right, so come and look here. So the first thing was we did this loop for all the enthalpy values. The loop's not going to work. I already got 3 of them on there. I'm just going to go ahead and write them out for the ones that I need. So what we're going to do, let's go ahead and just move my comment down here. And so enthalpy values, we already knew H1, so we can get H2. It's the enthalpy water, P equals P2, S equals S2. I need 3. Little time zooming here. Okay, don't need 4 because I already did that, but I need 5. So 5, and I think I need 6. So look it up at 6. Okay, it already did 7, and then I think I need 0.8, and hopefully, oops, that should be all of my enthalpy values. Okay, so now I've got all the enthalpy values at all 8 points. So now we can go ahead and determine the efficiency of our cycle. So let's look at modifying that. I'll go ahead and get rid of those temperatures. If we want to do a TS diagram in a minute, we can do that. So let's look at our efficiency. And so we've got, first of all, the heat input, right? It's going to be between 2 and 3. The boiler and the reheater is 5 and 4. And in fact, that doesn't change. Oh, no, actually it does, because 2 to 3, 4 going to 5, notice we're only reheating the fraction 1 minus y. So actually, Q in over here, it's not going to be that. We're only going to be doing 1 minus y, because we're pulling off a fraction y there. Yep, so 1 minus y is going through H5. So I'm going to look at this diagram. If we're pulling y down into my feed water heater, 1 minus y is going into 4. So only 1 minus y is getting reheated. And then if I look at the heat output, only 1 minus y is coming back through 5. 1 minus y is going through the condenser. So Q out, we're also going to be weighting by 1 minus y. So let me go ahead and do that. Oops. This will be 1 minus y. And it looks like we've got one more change. Okay, so the heat output with this new one, we're now going 6 to 7, not 6 to 1. So we want to put 7 in there. And let's see if that works. We need to make sure we get that fixed up. Okay, and all right, so now we've got an efficiency of 37.23%. Let's compare what we did last time. We had 35%, so we've increased 2%, which is it's a thermal increase of 2%, but it's almost a 8 or 9% increase in how much you were getting before. And it turns out that actually the more oops, I got the wrong version on there. Let me show you here. Okay, the more heat you start throwing through that feed water heater, you can actually increase your efficiency. In fact, we could go ahead and increase it from more than 20%. So maybe go ahead and put it up to say 30%, and we see go to 38%. So you might wonder, well, how much can I do? And in fact, we could actually look at the effects of that. So I'll show you one more thing here. What I'm going to do, I'm going to go ahead and comment out that Y, and what we're going to do is I'm just going to have EES go ahead and give me what all the efficiencies are for a bunch of different values of Y. So we're going to go ahead and create we want a parametric table, table. So we're going to create a parametric table, and what I'm going to do is I'm essentially going to say for a bunch of values of Y, go ahead and calculate what all the values are for eta. So I'm going to select the Y and eta variables here. So it gives me this table of, oops, pull that back up again, parametric table. Okay, so it just defaults to 10. You can do as much, it's like a spreadsheet, and so essentially you can put a bunch of values in for Y that you want, and it's going to solve the values for eta. So in fact, I could go ahead and just say, go ahead and give me for all the values of Y from say 0.95 to 0.05 to 0.95, right? Just to give a nice big range of values here. And now I'm going to go ahead and solve this table. Now remember, I had to comment out the value of Y in my variable here because it's going to grab all these values of Y to solve for it. And so, whoops, I got a little error here. Let me see. I don't know why that happened. 0.05. This should work. Okay. Unit system, not a big deal. Okay. So here what we see. If I was to pull just 5% off at Y, I'd get to an efficiency of 35%. And as I continue to increase it, if I go up to like 95%, I get a thermal efficiency of 44%. So you're getting up there like Brayton cycles, which are really good. Now there's a limit to how much you can pull off of that, or not a limit, but at some point you're just running everything through there. And you're not really generating much power. So your efficiency is good, but you're actually not putting much Q in because you're just kind of dumping it all back inside. So normally in practice, there's going to be like 10 or 20%. You're going to be over here. You're increasing your thermal efficiency several percent, which is going to be a 10 or 15% increase in how well it's working with a simple feed water heater. Also with all that piping, you're going to have pressure losses, so you don't want to run too much through. So from a practical point of view, it's it. But theoretically, you could go up and you could essentially go all the way up to one. If I did 1, then you actually end up with the Carnot efficiency for it. So okay. So what we did here is we went ahead and we solved all the problems that we were looking at before. All right, we were looking at the simple Rankine cycle. We went ahead and added the reheater on it to go ahead and pull it out of the saturation region, the mixture region, so we're not getting the bullets flying through our turbine. And then the last thing that we did is we went ahead and looked at putting a feed water heater in there to go ahead and increase our efficiency. So, okay, well, hopefully that helps you get prepared for the test. Good luck this week, and I will see you when I see you next.